or flexure. So today it is the rest of it, the design of two-way slabs for shear. And as I mentioned yesterday, I still hope there will be time left over today to pick up the two design examples, development length design examples that we did not have time for the other day. And then the question and answer session will be on everything we covered today, the two-way slabs for shear and the development length examples, anything related to that. Okay. So the first thing we say here is shear is typically not critical where a two-way slab system is supported on beams and or walls. So beam-supported slabs, this is typically not a problem. However, shear can be critical for flat plates or flat slabs directly supported on columns. Shear strength. So what the middle sentence I have been telling you from the beginning, that two-way shear or punching shear is a problem with flat plates. Shear strength at an exterior slab column connection is especially critical because the total exterior negative slab moment must be transferred to the edge column. This we have discussed. So at the exterior support section, even when there are no lateral loads, the slab moment at the exterior support section has to be transferred to the column. Part of that moment transfer is by flexure, but the remainder of the moment transfer is by shear. This punching shear due to moment transfer adds to punching shear caused by gravity, and that's where we have a potentially serious problem. This is something I went over, I believe, yesterday. I think it is important enough that I would like to repeat it briefly. This is what we just discussed. The blue lines, well, first of all, we have here a slab strip, a design strip of a slab as discussed yesterday, continuous over several columns. And the slab is subject to gravity only. The blue lines show us the bending moment diagram. At the exterior support, this entire slab moment has to be transferred to the supporting columns. And that moment transfer, as I discussed, is partly by moment, partly by shear. By the time we have arrived at the first interior support, the unbalanced moment is the difference between the bending moment to the left of the support and the bending moment to the right of the support. So there isn't a whole lot of moment to be transferred. At the second interior support, there is no moment to be transferred. The bending moment to the left of the support is the same as the bending moment to the right of the support. However, when the same slab system is subject to lateral loads due to wind, earthquakes, or whatever, the bending moment diagram due to the lateral loads is now shown by these blue lines. And now at every interior support, the unbalanced moment is the sum of the moments to the left and the right of the support. So under lateral loads, it is not just at the exterior support section, but at every support section, there is significant moment transfer. This is a huge difference between a slab that is subject to that supports gravity loads only, and a slab that also is used to resist wind or earthquake forces. Two types of shear are checked for flat plates or flat slabs directly supported by columns. One-way shear, which is beam type shear, and two-way shear, which we typically refer to as punching shear. One-way shear, under one-way shear, or when we design for one-way shear, we assume that a slab acts as a wide beam spanning between columns. Okay, this is so designed for one-way shear, even though we are designing a flat plate, is pretty much the same as the shear design of a beam. Critical section is taken at a distance d, effective depth of the slab, away from the column face. So critical section is 1d away from the column face, as it is in the case of a beam. Two-way or punching shear, failure line occurs along the surface of a truncated cone or pyramid around a column. Okay, so the failure surface looks like this. I think it is easy to visualize. This picture shows you the same thing. Now, these angles are, up to us to assume, and there are assumptions built into how we design by ACI, but we will get there gradually. So failure line occurs along the surface of a truncated cone or pyramid around a column. Critical section is taken at a distance d/2 from the face of the column. So the critical section for two-way shear is, so if you assume this is about 45 degrees, halfway from here to there would be the distance d/2. Okay, so imagine, so this is the column, the critical section is all around the column, a distance d/2 away from the column. You will see in plan view, this is the column. The critical section looks like this, critical section for shear, all around the column, and a distance d/2 away from the support face. Now, this critical section has a thickness equal to the thickness of the slab, or the effective depth of the slab. Okay, so I do not know how to describe it. This is strictly speaking not a section. Okay, the plan looks like this, but the critical section has a thickness through the slab. So critical section is taken at a distance d/2 from the face of the column. Two-way shear is usually more critical than one-way shear, as I've been telling you for quite some time now. Okay, so the main thing you need to understand is that the critical section is as thick as the wall and is all around the column. So the critical section for one-way shear is here, 1d away from the support face, and the load that causes one-way shear is the entire load that sits on the slab on the hatched portion outside of the critical section, from the critical section to the panel center line. Two-way shear is caused by slab load acting on the entire panel, center line of panel to center line of panel, from top to bottom, center line of panel to center line of panel, from right to left. So the two-way shear, the shear itself, is the entire load that sits on the slab panel minus the load that sits inside the critical section. The load that sits inside the critical section is directly on top of the support, so that does not cause any shear. That goes directly into the support. So when no or insignificant moment is transferred from slab to column, direct shear, which is distributed uniformly around the critical shear perimeter B/0, occurs around slab column joints. So the critical section, which is all around the column, the total perimeter of that is denoted by B sub 0. Okay, so the four sides added together is B sub 0. And we are saying that if there is no moment transfer, the shear stress is caused by this two-way shear. All the loading sitting on the hatch portion of the slab will cause uniform shear stresses on the four faces of the critical section. Okay, there is really no basis for thinking anything else. So when no or insignificant moment is transferred from slab to column, direct shear, which is distributed uniformly around the critical shear perimeter B sub 0, occurs around slab column joints. When significant moment is transferred from slab to column because of unbalanced gravity loads on either side of an interior column or horizontal load, shear transferred from unbalanced moment in addition to direct shear should be considered as we are about to do, and we actually skirted around that topic yesterday. So the direct shear causes uniform stresses on the four faces of the critical section, but this unbalanced moment causes additional shear stresses on the right face of the critical section, takes away from the shear stresses on the left face of the critical section. So then we are left with this kind of a shear distribution. If it is an exterior column, there are no shear stresses on the free face. Okay. Now there are three faces to the critical section. The direct load, the direct shear, causes uniform shear stresses on the three faces of the critical section, but the unbalanced moment adds to the shear stresses on this face of the critical section. So we end up with the stress distribution that you see in the figure. And this maximum stress on this face has to be within the stress carrying capacity of the concrete. Otherwise, we have to provide shear reinforcement and things like that. Okay. So ACI and BNBC provisions for slabs and footings. The shear strength of slabs and footings in the vicinity of columns, concentrated loads or reactions is governed by the more severe of two conditions. You will see this language throughout the code, not just columns. Columns, concentrated loads or reactions. Anyway, so two conditions: beam action, where each critical section to be investigated extends in a plane across the entire width, as you saw in our picture. Okay, the critical section goes across the entire width. So the shear strength is governed by the more severe of two conditions. One is beam action, where each critical section to be investigated extends in a plane across the entire width. This is one. The other is for two-way action. Each of the critical sections to be investigated shall be located so that its perimeter B sub 0 is a minimum but need not approach closer than D over 2. So there is potentially more than one critical section for two-way shear. Okay. So each of the critical sections to be investigated shall be located so that its perimeter B sub 0 is a minimum but need not approach closer than D over 2. So that is the technically what the critical section is. If it is a rectangular column, we take four faces to the critical section, which is an approximation, if you like, of this statement. Located so that the perimeter B sub 0 is a minimum but need not approach closer than D over 2. 2 says, so D over 2 from edges or corners of columns concentrated loads or reactions. And so the first critical section is around the column. But if you have a drop panel, a thickening of the slab, drop panel or shear bracket, whatever, so around the change in thickness where the drop panel ends, we will have a second critical section d/2 away from the faces of the drop panel. Okay. Now, at the first critical section around the column, the D effective depth is based on the thickness of the slab, including the drop. At the second critical section around the drop panel, the D is based on the thickness of the slab itself. Okay, so there is a critical section around the column. There is a second critical section where the slab thickness changes. If there is another step in the thickness, then we have potentially another critical section. Okay, so that is what is said on that slide. So the first critical section, as you see, is here. As I indicated to you, the D is based on the thickness, including the drop. And there is a second critical section around the drop panel. And now the thickness is based on the thickness of the slab itself. Okay. So I think this is pretty clear cut. This is a circular column with a column capital. The column capital, as I mentioned yesterday, is part of the column, not part of the slab. Drop panel is part of the slab. The column capital is part of the column. So now the only critical section is around the column capital. There is no criticals, and there is no second critical section around the column. Okay, that's kind of important. The perimeter again is B0. Here, what you see is this is the column, and then there is shear reinforcement. That is shear reinforcement. Okay, this is longitudinal reinforcement in the slab. And because shear is high, we have provided shear reinforcement. There is a first critical section around the column itself, and then there is a second critical section around where the shear reinforcement has been discontinued. As you move away from the column, the slab shear decreases. Okay, remember, shear is the load sitting on the slab minus the load sitting inside the critical section. So if the critical section faces are away from the column, there will be less punching shear. And so at one point, we will be able to discontinue the shear reinforcement. And around that, around the section where the shear reinforcement is discontinued, D/2 away from that, we will have another critical section as outlined by the dotted lines. Here, we have what is called shear head, structural steel shapes built into the slab. This I will not discuss. In my opinion, that has now become kind of obsolete. However, this is very important. The welded, the headed shear stud reinforcement. I will talk quite a bit about it. Anyway, there is the column, and then there is headed shear stud reinforcement. These are called stud rails. The story here is where the reinforcement is discontinued. Around that, there is a critical section to be considered. Okay, so and this headed shear stud reinforcement, as I said, we will talk quite a bit about. Critical section for shear. For slabs of uniform thickness, it is sufficient to check shear on one section. For slabs with changes in thickness, such as drop panels or shear caps, it is necessary to check shear at several sections, as we just discussed. For edge columns, where the slab cantilevers beyond the column, the critical perimeter will either be three-sided or four-sided. This is kind of an interesting situation. So for edge columns where the slab cantilevers beyond the edge, if the slab does not go beyond the edge, then we have a three-phase critical section, as I already showed you. The free face does not have shear on it. But if there is a cantilever, then just a little bit of cantilever, nothing will change. But if the cantilever is wide enough, then at one point it would make sense to consider a fourth face to the critical section. Now, where do we get to that point? So this is the column, and this is the slab that has extended beyond the edge of the column. So this is the cantilever. Here we are saying if the cantilever width or whatever, the overhang of the cantilever is smaller than or equal to this column dimension by 2 plus the effective depth, then we have just three faces to the critical section as shown in this picture. However, if the overhang is larger than this column dimension divided by 2 plus the effective depth, then we have four faces to the critical section. I should have made acknowledgement. This is from a publication by the Concrete Reinforcing Steel Institute, CRSI. This is where I took it from. I think it makes some basic sense, but I do not know what the basis is to the specific recommendations. Anyway, this is the only thing I could find where there is a guidance as to when there are three faces to the critical section or four faces to the critical section when your slab cantilevers beyond the edge. For square or rectangular columns, concentrated loads or reaction areas, the critical sections with four straight sides shall be permitted. So nobody is saying that that's what you have to do, four faces parallel, because remember, the exact language is B sub 0 shall be minimum and shall not approach closer than D over 2 to the column or reaction area. So that if you try to literally, what I want to say is, at this corner, you have gone more than D over 2 from the corner of the column. So this four-phase critical section is not exactly what is described by this language, but the code is saying that the four-phase critical section is good enough. For square, rectangular columns, concentrated, etc., the critical sections with four straight sides shall be permitted. That's totally officially good. Okay, so we have talked about the shear, the required shear strength V sub U quite a bit. That's the load sitting on the slab panel outside of the critical section. But what is the shear strength? How much punching shear can concrete resist? So the design, anyway, I think you can read it. So the V sub N nominal shear strength, as always, has two parts to it. V sub C, the punching shear that concrete itself can carry, and V sub S, the punching shear that is carried by any shear reinforcement that we may decide to provide. The punching shear that concrete itself can carry, V sub C, is given in ACI 318 and BNBC 2020 by three different expressions, and the smallest value governs. So you shall calculate B sub C by three different expressions, and you will take the lowest of the three values that you calculate. Okay? The first of the expressions is here. B sub C is a constant times 1 over 2, 1 plus 2 over beta. Beta is the long side to the short side of the column. Okay? The longer dimension to the shorter dimension ratio for the column. Yeah, lambda is the lightweight concrete factor. For normal weight concrete, it's 1. F sub C prime, you know. B sub 0 is the perimeter of the critical section. D is the effective depth. Beta is the ratio of long side to short side of the column, concentrated load or reaction area. The second expression is here. Now there is an alpha sub S, which is 40 for interior columns, 30 for edge columns, 20 for corner columns. Then D, B sub 0, everything else in that expression you know. So that is the second expression. This is the third expression. A constant times lambda, the lightweight concrete factor, square root of F sub C prime, B sub 0, the perimeter of the critical section, and D, the effective depth. Okay. Now, the long side to short side ratio for a rectangular column, it is quite simple. But if you have a column of this kind of a shape, then the long side to short side ratio is not simple. Anyway, this picture gives you an idea as to how to figure out the long to short side ratio for column shapes that are not all that terribly conventional. Okay. Now, so of the three expressions that you saw for B sub C, in the first expression, B sub C was a function of beta, the long side to short side ratio of the column. And that expression gives you shear strength. So on the x-axis is 1 over beta, not beta. So 1 over beta would be the short side to long side ratio. Okay. And on the y-axis is B sub C, that is non-dimensionalized, however you call it, normalized. Okay. So you see that the B sub C varies between 2 and 4 square root of F sub C prime. Now, 2 square root of F sub C prime requires a short to long side ratio of 0 or a long to short side ratio of infinity. So that is not practical. Normally, you will be at 4 square root of F sub C prime or a little bit less. Obviously, if you go higher, then this is the cutoff. You cannot go, remember, it is the smallest of three expressions. Anyway, this is the influence of beta on B sub C, and this is the influence of, in the second expression, we have alpha sub S and B sub 0 over D. B sub 0, the perimeter of the critical section, divided by the effective depth. Again, we have taken the reciprocal of that. Instead of B sub 0 over D, we have taken D over B sub 0. On the y-axis is B sub C. And you see the influence of whether it's an interior column, an edge column, a corner column, influence of that, and also the influence of this B sub 0 over D ratio. Obviously, we can never go above 4 square root of F sub C prime. This again is 2 square root of F sub C prime. For practical situations, you will not fall far below 4 square root of F sub C prime. Now, shear reinforcement consisting, so that is the concrete part, B sub C. Now, shear strength provided by bars, wires, and single or multiple leg stirrups. So, shear reinforcement consisting of bars or wires and single or multiple leg stirrups shall be permitted in slabs and footings with D effective depth greater than or equal to 150 millimeter. This came up in discussion yesterday, remember? And I said I thought the minimum thickness was 6 inches or D or some function of the bottom. Anyway, so it is actually 6 inches. In thinner slabs, you will not be allowed any shear reinforcement. But shear reinforcement shall be permitted. Shear reinforcement consisting of bars or wires and single or multiple leg stirrups shall be permitted in slabs and footings with D greater than or equal to 150 millimeter, but not less than 16 times the shear reinforcement bar diameter. So if the slab is thinner than 16 times the shear reinforcement bar diameter, okay, bar diameter, let us say is 1200, and so 16 times 12 would be 192, I think. So if the slab thickness is less than 192 millimeters, you will not be able to use 12 millimeter diameter shear reinforcement in the slab. So this minimum thickness is kind of important. Shear reinforcement shall be in accordance with section such and such. Okay. So these are typical shear reinforcement in a slab. Okay, I think the pictures are graphic enough. This closed stirrup is a pretty solid way to go. But all this shear reinforcement is labor intensive, and right now in this country, this is, I don't want to say this is obsolete, but this is seldom used. What has taken over is the headed shear stud reinforcement, which is a whole lot simpler than all of this. Okay, but this is fully permitted. Now, when we use shear reinforcement, conventional shear reinforcement, as you saw, if you'd give me just 30 seconds, I have to shut off the sound that is coming in. There was sun in my eyes and I could hardly see the screen. Okay. So V sub n nominal shear strength again is V sub C plus V sub S. Now, when this is very important, when there is no shear reinforcement, concrete is good for about 4 square root of F sub C prime. The three expressions that you saw, okay, you can never exceed 4 square root of F sub C prime. The other two expressions may give you a little bit less, but you are about 4 square root of F sub C prime. In your units, 0.33 square root of F sub C prime. That's what concrete is good for. But when we use shear reinforcement, conventional shear reinforcement, I should say, shear reinforcement that I showed you pictures of, now P sub C is assumed to be 2 square root of F sub C prime, half of what concrete can carry in the absence of shear reinforcement. Okay, this is extremely important. So concrete now carries 2 square root of F sub C prime, and the remainder of the shear has to be resisted by the shear reinforcement. V sub S has to be good for the rest of the shear. Okay, so V sub N is V sub C plus V sub S. V sub S is given by this expression that you have seen before for beam design, but there are a couple things that are kind of important. A sub V shall be taken as the cross-sectional area of all legs of reinforcement on one peripheral line that is geometrically similar to the perimeter of the column section. So if you I don't know that I have a picture this way. No, I have to show you a picture because this is the crucial thing. Okay, is this good enough for? Yeah, let's use this. So these are the stirrups, and V sub S would, so this stirrup has vertical legs. We are looking at the plan, but the stirrups have vertical legs. Remember the other picture, those were wrapping the okay. So these legs resist shear. Okay. Now there are four. So this is the column. If you take a line here all around the column, you will get 8 legs of stirrup, and the combined area of those 8 legs would be the A sub V. That's what this language is telling you, and please pay attention to that. A sub V shall be taken as the cross-sectional area of all legs of reinforcement on one peripheral line that is geometrically similar to the perimeter of the column section. Okay. The other thing is the total V sub C plus V sub S. V sub C, remember, is 2 square root of F sub C prime. The total V sub C plus V sub S cannot exceed 6 square root of F sub C prime. So with conventional shear reinforcement, that is the upper limit to the shear that you can carry, 6 square root of F sub C prime. Okay. Then there are quite a few details given of the shear reinforcement. The distance between the column face and the first line of stirrup legs that surround the column shall not exceed d over 2. So this distance shall not exceed d over 2. I don't know that I need to go pictures, but okay. So the distance between the column face and the first line of stirrup legs that surrounds the column shall not exceed d over 2. The spacing between adjacent stirrup legs, now not the stirrups, the spacing between stirrup legs in the first line of shear reinforcement shall not exceed 2d measured in etc. etc. So the distance between shear legs shall not exceed 2d. Sorry. Okay, the spacing between successive lines of shear reinforcement that surround the column shall not exceed d over 2, which is totally understandable. Then slab shear reinforcement shall satisfy the anchorage requirement. So like any shear reinforcement, the reinforcement, whatever you use, the stirrups, whatever, they have to be developed. Okay, there are these three figures tell you about the layout, if you like, of conventional shear reinforcement. The first picture is at an interior column, the second picture at an edge column, the third picture at a corner column. Okay, now the headed shear stud reinforcement. This was brought into ACI 318 in the 2008 edition, the edition that you are dealing with. Okay, up to 318.05, this type of reinforcement was not in ACI 318 because this headed shear stud reinforcement was a proprietary item. Okay, it like you had to pay somebody a royalty to use this product because they had a patent on it. Then the patent ran out, and when a patent runs out, obviously nobody can claim royalty. And then there were multiple manufacturers, and then ACI 318 felt comfortable in bringing it into the code. Proprietary products are not covered by ACI 318 for obvious reasons. Okay. And I would say since before that happened, even when it was proprietary, the headed shear stud reinforcement started rapidly replacing conventional shear reinforcement. Now, this is pretty much all punching shear reinforcement that is used in slabs. Okay, basically all. There are, I'm sure, exceptions, but this is by far the most common type of punching shear reinforcement because of its many advantages. So headed shear stud reinforcement placed perpendicular to the plane of a slab or footing shall be permitted in slabs, etc. This is what it looks like. These are called stud rails. This is a thin metal strip. These studs are welded to the metal strip or rail, whatever you want to call it. The studs have big heads. These are big, 10 diameter, something like that. Much bigger than the heads on a Nelson stud. Those big heads anchor the legs to the concrete, and when anchored, those legs resist punching shear. Okay, you basically have the vertical legs of the stirrups resisting shear for you. The you get the picture, I'm sure. Okay, so so these are the stud rails. There are 8 rails used here at an interior column, and this is a situation where post-tensioning ducts have been placed. The structural integrity reinforcement that I was discussing the other day, you see the post-tensioning cables going through the column cage, and it goes underneath the perpendicular cables. All of that is illustrated here. Anyway, here you see real use of this headed shear stud reinforcement. The overall height of the shear stud assembly shall not be less than the thickness of the member less the sum of some of these details I'm going to let you read because it probably on register, and I do not know. I would like to have some time for the development examples. So by going through these details, I do not know that I'll improve anything. Okay. Headed shear stud reinforcement was introduced in the 2008 code, as I already mentioned. Using headed stud assemblies as shear reinforcement in slabs and footings requires specifying the stud shank diameter, the spacing of the studs, and the height of the assemblies for the particular applications. This is what the engineer has to specify. Tests and the references to a Joint Committee 421 report show that vertical studs mechanically anchored as close as possible to the top and bottom of slabs are effective in resisting punching shear. The bounds of the overall, the rest of it, I'll let you read, okay? Including the two pictures. My spending time here will not will not improve anything. Now, very, very importantly, remember, I'll go back. So in the absence of any shear reinforcement, concrete is good for 4 square root of F sub C prime of punching shear strength. When we have conventional shear reinforcement, concrete is good for 2 square root of F sub C prime, and the upper limit maximum V sub C plus V sub S is restricted to 6 square root of F sub C prime, 0.5 in your units, 0.5 square root of F sub C prime. When we use headed stud reinforcement, concrete is good for 3 square root of F sub C prime, 0.25 in your units, okay? 3 square root of F sub C prime, and the total now is up to 8 square root of F sub C prime. So the maximum shear that we can carry goes up from 6 to 8 square root of F sub C prime, from 0.5 to 0.66 square root of F sub C prime. So this is a huge advantage of the headed stud reinforcement, in addition to the ease of placement and so forth. This is so much easier and cleaner than the stirrups and things that we used to use. Okay, V sub S shall be calculated using this equation below, with A sub B equal to the same thing as for the legs of the stirrups. A sub B equal to the cross-sectional area of all the shear reinforcement in one peripheral line that is approximately parallel to the perimeter of the column section, where S is the spacing, etc. Okay, so the A sub B, the best will be the picture maybe. Maybe not. So this is the column, and so the first line that is parallel to the column will cross 8 of those legs, 2 legs here, 2 legs there, 2 legs there, and 2 legs here. The total cross-sectional area of the 8 legs is the B sub A sub B. That is in equation 15, whatever the number was. Okay, so A sub B is the total area of those 8 legs. Take a look at the writing and you will see. Okay. This A sub V F sub YT divided by B sub 0 S shall not be any less than 2 square root of F sub C prime. Okay. Where S is the spacing of the peripheral lines of headed shear stud reinforcement, A sub V F sub YT divided by B sub 0 S shall not be any less than 2 square root of F sub C prime. That is a limitation that is placed. The spacing between the column face and the first peripheral line of shear reinforcement shall not exceed D over 2, As in the case of conventional shear reinforcement, the spacing between peripheral lines of shear reinforcement measured direction shall be, so the spacing between peripheral lines of shear reinforcement shall be constant. Okay, you will not keep on varying that. So we are still talking about shear strength provided by headed shear stud reinforcement. For pre-stressed slabs or footings, the spacing shall not exceed 0.75 D. So here we say the spacing shall be uniform. The spacing between peripheral lines of shear reinforcement shall be constant. Then we are saying for pre-stressed slabs, this spacing shall not exceed 75% of D. For all other slabs, the spacing shall be based on the value of the shear stress due to factored shear force and unbalanced moment at the critical section defined. So you will figure out the spacing based on the amount of shear that you have to deal with, but shall not exceed 75% of D, where maximum shear stress due to factor loads are less than or equal to 0.5, that is 6 square root of f sub c prime, and 50% of D where maximum shear stress is more than 6 square root of f sub c prime. So the summary of all this is the spacing of the stud legs, first of all, shall be uniform, shall be the same. Okay, that's what the previous slide said. This spacing for pre-stressed concrete, which are post-tension slabs, shall not exceed 75% of D, period. Okay. If it is conventionally reinforced slab, there is no post-tension, then the spacing shall not exceed 75% of D if the shear is less than or equal to 6 square root of f sub c prime, and the spacing shall be reduced to 50% of D if the shear is more than 6 square root of f sub c prime. That's the sum of everything that has been said. The specified spacing between peripheral lines of shear reinforcement are justified by experiments that are reported on in that committee, joint committee report. The spacing between adjacent shear reinforcement elements so the spacing between adjacent shear reinforcement elements measured on the perimeter of the first peripheral line, etc. So that this basically means the spacing between the legs shall not exceed 2D. This is the spacing is along the rail, and this is the spacing between the two rails, or the spacing between two legs of the same arm of shear reinforcement shall not exceed 2D. Shear stress due to factored shear force and moment shall not exceed 2 square root of f sub c prime at the critical section located D over 2 outside the outermost. This is kind of important. So where, let me go. I think I have to go quite a ways back. But this is important for you to understand. This is not just shear stud reinforcement. This is with conventional shear reinforcement also. Let me find. No. Okay, this is good enough. Now, whether you have conventional reinforcement or the stud rails, stirrups or stud rails, at this critical section, around where the shear reinforcement has been left off, at that critical section, the shear shall not exceed 2 square root of f sub c prime. Okay, we are not, we cannot say that now there is no reinforcement, so the concrete is good for 4 square root of f sub c prime. No, at that critical section, the shear shall not exceed 2 square root of f sub c prime. That is something you absolutely need to understand and practice. Okay, so there are a lot of details here that, yeah. So this picture is what I'm talking about. Okay, at that critical section, the shear shall not exceed 2 square root of f sub c prime, 0.17. Oh, the picture was right afterwards. Okay. So shall not exceed 0.17 square root of f sub c prime at the critical section d over 2 outside the outermost peripheral line of shear reinforcement. Okay. So this, I thought the picture was before. Anyway, so this picture gives you, just as with the conventional shear reinforcement, the different layouts that you are likely to have here for interior column and exterior or edge column and a corner column. Okay, here there are 8 rails that are used. Here there are 6 rails. Here there are 4 rails that are used. Okay, next topic is openings in slabs. When openings in slabs are located at a distance less than 10 times the slab thickness from a concentrated load or reaction area, or when openings in flat slabs are located within column strips, the critical slab sections of shear shall be modified as follows. I think, let me cut through the language. So this is what it is. If you have an opening within 10 times the slab thickness from the center of the column, then you will draw lines that are tangent to the opening. However, they're described in the code. You can read the language. And so this is the critical section. This is the critical section. The part of the critical section that is inside those lines, you will ignore that in shear computations. That doesn't exist for you. Okay, so the critical section will start from here and start from here. Are you with me? So that part of the critical section does not work for you. Same thing about this opening. Okay, the critical section from here to there does not work for you. So I think this picture tells you everything that you need to know. So this is what was being described by the language that I started reading and then I didn't read. Okay, so this is how you deal with openings in slabs. Now comes the big topic of transfer of moment in slab column connections. ACI considers transfer of moment between a slab and a column a critical section for shear due to moment transfer is d over 2 from the face of the column, which is the same critical section for direct two-way shear. So there is no difference in critical section when you are dealing with the direct shear, punching shear, or shear transfer, punching shear due to unbalanced moment transfer. The total shear stress due to direct shear and shear caused by moment transfer is given by this expression. Okay, let me. Okay, and I'll Okay, this is I don't know which figure to. 1 second. Yeah, this is probably good enough. Okay, so the V, so there were two parts, V over A sub C. A sub C is the area of the critical section. So if it is a three-sided critical section, it is the total area of the three faces. If it is a four-faced critical section, A sub C is the total area of the four faces of the critical section. Okay, so that is the direct shear part, V sub U divided by A sub C. Now the part of the unbalanced moment that is transferred by shear, gamma sub V times M sub U, that causes shear stresses on the, let us say, the right face and the left face of the critical section. No shear stress on the front face and the back face, okay, which is equal to this moment divided by the polar moment of inertia of the critical section. This is a critical section with four faces with a hole inside. Okay, so it is not moment of inertia, it's a polar moment of inertia multiplied by the distance from the polar moment of inertia to the face. This is like m over I times y, but this is an annular section. There are four faces with a hole inside. So that four-faced or three-phase section has a polar moment of inertia about the centroidal axis, which we will have to determine, and the stress on the faces would be the part of the unbalanced moment that is transferred by shear divided by the polar moment of inertia multiplied by the distance. Okay. So this is what we are saying. M sub U is unbalanced moment. C is distance from centroid of critical section to face of section where stress is being computed. J is property of critical section analogous to polar moment of inertia. So this is let's take the interior. This is the critical section. Okay, we will calculate a J about the critical section, and I'll show you formulas and things, and the moment gamma sub V times M sub U divided by the polar moment of inertia J multiplied by the distance from the centroidal axis to the face will give us the stress on this face. So stress on this face will be in the direction of shear caused by gravity. On this face, the direction of the shear due to moment transfer will be opposite to the shear caused by gravity. So on this face, the shear caused by the stress caused by direct punching shear will be decreasing, and on this face, the shear due to punching shear will be adding to the shear caused by the stresses due to the moment transfer and the direct shear will be additive on this face. So this is what I was trying to say. I think the pictures are more graphic. Okay, so so the total shear will be the total shear stress will be the shear caused by the direct shear, the stress caused by the direct shear, and the stress caused by the moment transfer, the part of the moment transfer that takes place by shear. Okay, when gravity, this language we have gone through, I think, probably yesterday. When gravity load, wind, earthquake, or other lateral forces cause transfer of moment between slab and column, a fraction of the unbalanced moment shall be transferred by flexion. The fraction that is carried by flexure is given by this expression. By now you know what B sub 1 and B sub 2 are. The dimensions of the critical section, B sub 1 in the direction of analysis, B sub 2 in the perpendicular direction. For a square column, this gives us 60% for gamma sub f, 0.6. For a rectangular section, we get something close to 0.6, but not equal to 0.6. Okay. For non-prestressed slabs with unbalanced moment transferred between slab and column, it shall be. So this is the part that I emphasized yesterday that Jacob Grossman brought into the code, some flexibility. So at the edge column, if we have a gamma sub f of 0.6 because we have a square column, that 0.6 can be increased all the way up to 1. We can transfer the entire unbalanced moment by flexure, leaving nothing to be transferred by shear if the V sub u, we know V sub u by now, the required shear strength. V sub u is the required shear strength without any moment transfer. If V sub u is less than or equal to 75% of phi times V sub c at an edge column. If it is a corner column, then we can do the same thing. We can increase a gamma sub f of 0.6 all the way up to 1 if V sub u is less than or equal to 0.5 times phi V sub c. This is great flexibility because if 100% of the unbalanced moment is transferred by flexure, there is no unbalanced moment to be transferred by shear. Okay? So when it comes to shear design, we are so much better off. If it is an interior column or an exterior column, but the bending now is parallel to the edge. So an interior column or an edge column where the bending is parallel to the edge, now gamma sub f cannot be increased all the way to 1, but it can be increased to 125% of the calculated value of gamma sub f. Okay. If gamma sub f is 0.6, we can increase it all the way to 0.75, 125%. If two things are true. If V sub u now is less than 40% of phi times V sub c, no longer 50 or 75. Secondly, the tensile strain, the net tensile strain calculated for the effective slab width that we discussed yesterday, the moment transfer band width. The net tensile strain calculated for the effective slab width shall not be less than 0.010. Okay, if those two conditions are satisfied, then we can increase gamma sub f to 125% of gamma sub f. Again, that gives us flexibility. I showed you numbers yesterday, so that should be still fresh on your minds. Okay, so what is shown on this picture we have discussed already. So this is the combined shear stress due to direct shear and the unbalanced moment transfer. The stress distribution is assumed as illustrated in the figure that I just showed you for an interior or exterior column. The perimeter of the critical section ABCD is determined. I think this you can read. Okay, so this is to make it more specific, if you like. Okay, so we had the general expression before. Now we are making it more specific to the right face and the left face. The right face is AB, the left face is CD in the picture. Okay, so the specific expressions are V sub U on the right face is P sub E over A sub C. We know what A sub C is. The moment transfer by shear, that's gamma sub V times M sub U divided by the polar moment of inertia. We are calling it J sub C about the centroidal axis, and the distance from the centroidal axis to the face AB. Okay, here it is positive. On the right face, the moment transfer shear is additive to the direct shear. On the left face, the direct shear is the same as this, but now the moment transfer shear is, it takes away from the direct shear. And that shear is the unbalanced moment that is transferred by shear divided by the same polar moment of inertia multiplied by the distance from the centroidal axis now to the left face. Okay, so this is plus, this is minus, this is the distance to the right face, this distance to the left face. Gamma sub F we have discussed, and gamma sub B is 1 minus gamma sub F. The A sub C and J sub C, in order to do these calculations, we have to be able to figure those out. And to help you, I have reproduced from the PCA notes from ACI 318 the information you will need basically for all the situations that you will ever face. Okay, so there are 4 cases that cover almost everything. One is edge column, where bending is parallel to the edge. This picture, I think it is very easy to visually see. Okay, so this is the slab, this is an edge column, and bending is parallel to the edge. Case B is interior column, very simple. Case C is an edge column where the bending is perpendicular to the edge. And case D is a corner column. For all those cases, we have A sub C given in a formula. J over C, C is the distance from the centroidal axis to the right face. J over C prime, this is distance from the centroidal axis to the left face. The C and C sub prime. So everything that we'll need in our shear stress computation can be obtained from this table. The B, remember, is interior column, and C is edge column where the bending is perpendicular to the edge. So these formulas are the same as what you see in that table. So there is no point in spending time on that. So you can go directly from this picture. Okay, this picture tells you you need J sub C and C over B. It is always J over C. Okay, the J over C is in this expression J sub C over C sub AB, and J over C prime is J sub C over C sub CD. So from that expression, you can go directly to this table. You can calculate the properties that you need, and that gives you the stresses. And I will show you an example. It will come home. If you have a circular column, you can the critical section around the column is also of this shape. Okay, it has a circular perimeter and then the thickness, and you can do the same computations for that. I did that years ago, and the number should still be good. You can treat a circular section as a circular section, or you can take a equivalent equivalent square that is permitted by the code, and then you will do your computations accordingly. Something got messed up in the figure. We'll when the slide set is posted, we'll take care of that. Okay, now, so as far as flat plate design is concerned for punching shear, that's all that we need. And I will, as I said, show you an example. Okay. Now we are talking about factored shear in slab systems with beams. Let's. This is definitely not unimportant. Anyway, let's get into this. So beams with alpha L sub 2 over L sub 1 equal to or greater than 1. This alpha sub F1 we discussed thoroughly yesterday. So beams, so that means reasonably stiff beams. Beams with alpha sub F1 L sub 2 or L sub 1 equal to or greater than 1 shall be proportional to resist shear caused by factor loads on tributary areas which are bounded by etc. etc. So if we have all this notation was explained yesterday, so I don't know that we need to spend time today. All we are saying here, if it is a beam supported slab and the beams are reasonably stiff beams, as indicated by that alpha sub F1 L sub 2 or L sub 1 larger than or equal to 1, then we will consider shear on the white area to be resisted by that beam. Okay, the loading on that entire area of the slab is loading on the beam that causes shear in the beam, and we know how to calculate the how to design the beam for that shear. Okay, this is calculation we have all done forever. So beam supported slab, the shear on this area goes to this beam, the shear on that area goes to this beam, the shear on that area goes to this beam, and the shear on that area goes to this beam. And we design the beams, and everything is good. Okay. Now, this is what is a little bit of a what's the right word? This is something you may not always think of. So we are very used to flat plates, no beams, and then beam supported slabs where the beams are, without thinking, when we say beam supported slabs, we think of reasonably stiff beams. What if there are beams, but the beams are kind of flimsy? Okay, it's not a flat plate, but the beams supporting our slab panels are not stiff. So then ACI 318 is saying you can proportion down. So for alpha sub F1 L sub 2 but L sub 1 equal to 1, the shear that I showed you on the plan goes to the beam. What if alpha sub F1 L sub 2 or L sub 1 is 0.5? Then the suggestion is only half the shear goes to the beam. The other half of the shear has to be dealt with in the slab. Okay, so that is the kind of message that ACI 318 gives you. think about it, these cases I do not think are all that common. We either have flat plates or we have beam supported slabs where the beams are reasonably stiff. These in between cases, how you would deal with is the subject here. And maybe read a little bit and think, and you will see that there is nothing all that terribly complicated that is being suggested. This is still continuation of the same thought. If the supporting beams are not stiff enough, then how you would deal with the uh, the situation. Okay, that brings us to the shear design example, slab flat plate shear design example. I'm wondering whether to get into the example before. Let's take a 5 minute break right here. I think so. 31 minutes after the hour, we'll come back. I'll do this example and then go into the development length part and then question and answer. Okay.
Thank you, Dr. Gus. Yeah, I was about to tell you that we can have a break right now.
Good. Okay, it's 5 minutes are up, so we will get into the example. I I talked about sunshine in my face, so I thought that it might have sounded strange to you. For your information, it's 9:30 in the morning here in Chicago, and uh, I don't know if it is for your information or enjoyment or what. The temperature now is -6 degrees centigrade. -6 degrees centigrade. That's 14 degrees Fahrenheit. Well below freezing. This is without any wind. Just just imagine that and think how lucky you are. Okay. So with that, the same slab system as yesterday. 5.5 meters in one direction at the spans, 4.3 meters in the orthogonal direction. We are designing the strip in blue centered on an interior column line. The problem description is the same as yesterday, two-way slab system without beams, no edge beams, concrete strength 40 MPa, reinforcement 420, the unit weight of concrete 2400 kilograms by cubic meters. Columns are 400 by 400 millimeters. Live load 2 kilonewton per meters per square meter, that is reducible, and partition load 1 kilonewton per square meter, which is not reducible. The minimum thickness from table 9.5c comes to clear span divided by 30, clear span in the wrong direction, which is 5500 minus 400, and that gives us 170 millimeters. We used 200 millimeter slab thickness. The absolute minimum thickness required by 318 is 125 millimeters. That obviously we did not violate. The effective depth for 200 millimeter total thickness is 168 millimeters. We take away 20 millimeters of clear cover and the diameter of one number 12 bar. This itself is kind of significant. We are not taking away half a bar diameter, but a full bar diameter, because in a two-way slabs, we have two layers of reinforcement. If you are finicky, you could design the slab in one direction for so one layer will be below the other layer. So one direction of the slab, you could take D to the centroid of the lower layer, and in the orthogonal direction, you could take D to the centroid of the upper layer. I do not know anybody who does that. So we always take D to the intersection of the two layers. This is why it is the total depth minus the clear cover minus one bar diameter. Okay, that gives us 168 millimeters. The self weight of the slab, 200 millimeters deep, is 0.2 times 2400, the unit weight of concrete, multiplied by the value of G. That comes to 4.7 kilonewton per square meters. The uh, the live load reduction comes to 8.4% based on the tributary area of 23.65 square meters, which is 4.3 times 5.5. That gives us a reduced live load of 1.83 kilonewton per square meter, reduced from 2. That plus the partition load gives us a total live load of 2.83 kilonewton per square meters. So by the 2 by 1 load combination, the Q sub U is 6.58 kilonewton per square meters. The only other load combination that applies when loads are due to gravity only is that gives us 10.2 kilonewton per square meters. The larger one governs, so it is 10.2 kilonewton per square meters. Up to there, everything was covered yesterday. Now, first thing we will do is check for one-way shear. So 5.5 meter by 4.3 meters is our panel size. This is the column in the center. The critical section is 1D away from the column face. So it is the distance from the critical section to the column face is 168 millimeters. The one-way shear is the entire load that sits on this portion of the slab from the critical section to the panel center line. So that's what we are calculating here. 10.2 is the load in kilonewton per square millimeters. The distance from the critical section to the edge is 5.5 meters by 2. That is half the panel length. That takes us so half the panel length is 5.5 meters by 2 minus half the column dimension, 0.4 divided by 2 minus 0.168. Okay, so half the panel dimension would be from here to there. We took away half the column dimension and then that distance. It's pretty straightforward stuff. So, and the other dimension, the width of the panel is 4.3. So we are looking at 104 kilonewtons of one-way shear at that critical section. Okay. How much can concrete carry? One-way shear, the strength is 2 square root of f sub c prime. Very simple. So phi is 0.5. Then 2 or 0.17 lambda is 1, square root of f sub c prime is 40 to the power 0.5, and then the section itself, b sub wd, 4300 times 168. That gives us a one-way shear capacity of the concrete itself, design value already reduced by phi, of 583 kilonewtons. That is sufficient. That is way larger than 104. So that is okay. I actually have never seen one-way shear problem in a flat plate. We always check, but I have never seen any problem. Never. Okay. Now that was obviously at an interior column. Now we will check one-way shear at an edge column. Okay. So from the center of the column to the panel center line is half a panel width. That's 2.75 meters. So the shear, which is the load, factor load sitting on this portion of the slab from the blue line to the panel center line, is 10.2 is the load, 2.75 is from the center line of the column to the panel center line, minus half the column width, minus the distance from the column face to the critical section, and then the width of the panel. That gives us 104 kilonewtons of shear. Phi times b sub c, once again, is 2 square root of f sub c prime. That comes to 589. We are obviously well over the 104, so everything is good. Now, the two-way shear. This check right now is without any unbalanced moment transfer. This is just the direct shear. Okay. So this is the column. This is the critical section around the column. The distance from the face of the column to the face of the critical section is 1/2 of D. D is 168 millimeters, so this is 84 millimeters. Okay. I think you know all the numbers. The V sub U now is the load sitting on this entire slab panel outside of the critical section. So side dimension of square critical section is 500, and so this distance is 40 plus 84 this way, 84 that way, and that is 500 and 568 rounded to 570 millimeters. Factored shear at critical section. So 10.8 kilonewton per square meter is the load. Then the entire panel area is 5.5 times 4.3. These are in meters, minus the area within the critical section. Okay. So the idea is we are calculating the load that is sitting on the panel outside of the critical section. We are taking away the load that is inside the critical section. That is the 0.57 times 0.57. That gives us 238 kilonewtons of direct shear. This is very simply the factor load sitting on the entire slab panel outside of the critical section, 238 kilonewton meters. How much can concrete carry? Forgetting about any shear reinforcement. Okay. Three expressions. Remember, one is a function of beta, the long side to short side ratio. Another is a function of alpha sub S, which is 40 for interior columns, 30 for exterior columns, 20 for corner columns. And the third one is a straightforward 4 square root of f sub c prime. Beta in our case is 1. We have a square column. Alpha sub s, we are at an interior column. Alpha sub s is 40. And beta sub 0, B sub 0, the perimeter of the critical section, one side is 568. We took it 570 on the last page, same thing. Okay, 568. Each face has a length of 568 multiplied by 4 is the total perimeter. That's 2272 millimeters. So if we plug the numbers in, the first formula where B sub c is a function of beta gives us 1231 kilonewtons. Second formula where alpha sub s is involved, we get 993. And the third formula gives us 797. That obviously governs. The smallest one governs. So we have 4 square root of f sub c prime. 797 reduced by phi of 0.75 gives us 598, which is still larger than the required shear strength that we calculated of 238 kilonewtons. So if we do not consider, if moment transfer is not in the picture, we have sufficient punching shear capacity, more than sufficient. Okay? We do the same check at the edge column. Okay? So I think everything is familiar to you by now. The 84 millimeters. So the length of this face is now 484 millimeters, and this face is 568. So 484 and 568. Dimensions of critical section, yeah, as I just said, 484, 568. Factored shear at critical section is the load 10.2. Then the entire panel area is, so width remains 4.3, 5.5 by 2. So 5.5 by 2 is this distance, and then the edge distance from the center of the column to the edge, that's another 200 millimeters that is added. So we are going from the edge of the slab or column to the panel central line. So 5.5 by 2 plus 0.2 times 4.3 minus the load that is sitting inside the critical section, all of that gives us a required shear strength of 127 kilonewtons. We do the same computation of punching shear strength of the concrete. The beta is still 1.0, but alpha sub s changes to 30 because this is an edge column, and B sub 0 changes because there are only 3 faces to the critical section, comes to 1536 millimeters. The first formula gives us 832, second formula gives us 715, third formula gives us 539. All the numbers are smaller than for the interior column, as you would expect. And then that gives us design shear strength of 404 kilonewtons, which is sufficiently over 127 kilonewtons. So that tells us that the thickness of 200 millimeters that we chose is probably fine, although we now have to consider the unbalanced moment transfer. Okay. So direct design method can be used for this example. We checked that yesterday. Positive and negative moments at column and middle strips were determined using direct design method. The static moment, the free span moment, WL squared by 8, came to 142.6 kilonewton meters. None of this is new, so there is no point in spending time. And starting from that, we ended up with this table that is in your yesterday's handout. Okay, so end span, interior span, end span. We have column strip, middle strip, interior span. Also, we have column strip, middle strip. Now for the end span, we have exterior negative moment, positive moment, interior negative moment, middle strip, the same thing. But for the interior span, it is just positive and negative. Okay, so you remember 65-35 distribution and all of that. Now, total shear stress is the sum of the direct shear stress plus the shear stress due to the fraction of unbalanced moment transferred by eccentricity of shear. Assume shear stress due to moment transferred by eccentricity of shear varies linearly about the centroid of the section, as I showed you. Okay, so let me see one thing. Yeah, okay, very good. Okay. Okay, so a little bit of a twist or whatever you like, I don't know. Anyway, so now we will check the exterior support section for direct plus the direct shear and moment transfer. Okay, so this picture you have seen right now, there is absolutely nothing new. This expression is a little bit different, if you like, from what you saw earlier. So direct shear V sub U can be computed as follows. Okay? V sub U is Q sub U, the loading on the slab, multiplied by the area tributary to the column, minus so this is the load sitting outside of the critical section. So far, absolutely nothing different from what we have said before. Okay? So V sub U is the load sitting outside of the critical, load sitting on the slab panel outside of the critical section. The A here is 12.69 square meters, and B sub 1, B sub 2 is 484. The dimension B sub 1 is 484 meters. The dimension B sub 2 continues on the next, okay, and M sub 1, M sub 2, okay. The main point that I'm trying to make, the reason that I, on my screen, something comes on sometimes every few seconds that I have to decline. Okay, now it's coming every second now. Okay, this part is kind of new that we are introducing now, and this is what I would like to explain. Okay, so instead of saying V sub U is equal to just that, we are saying V sub U is this minus that. Okay, so let me try to explain this, and Bodhi kindly drew up this picture for me yesterday. So I thought without this picture, it will be kind of difficult to. So this is our slab continuous over 3 supports. Okay. We are at an exterior support. The loading on the slab is Q sub U. Q sub U causes a shear equal to that at this support, and the same at the other support, or if you consider the other side, that number may not be right, but there is a shear in this direction at that support. Now the bending moment at this section is M sub 1, and the bending moment at that section is M sub 2. This is a negative bending moment. This is a continuous support. This is also a negative bending moment because the slab is continuous over the support. That moment is definitely larger than that moment. So the two moments together will cause a shear M sub 2 minus M sub 1 that is directed this way at this support and directed the other way at the other support. Okay, we are considering the left support. So the shear at the left support is not just that, but also the shear caused by the two end moments. And that shear due to the end moments takes away from the direct shear, from this shear. Okay? So this is what we wrote. This is what we wrote here. And that part is important. Sometimes people do not bother about the moment, don't think about the moment, but you should. This is the right way to do it. Okay. So anyway, now we know all the numbers. The Q sub U is 10.2 kilonewton per square millimeters. A is shown here. The B sub 1 is the long dimension of the critical section. B sub 2 is the other dimension of the critical section. This is a square column in no. So one side is 484, the other is 568. I hope this is not a mistake. Yeah, 484. So that's right. 484 and 568 are the two sides. M sub 1, the M sub 1 I think I messed up with I call this one M sub 1, that one M sub 2. And then here, M sub 1 is, what is M sub 2 in the picture? The interior, the moment at the first interior support. Yeah, I should have. You see what I'm talking about. So that should have been M sub 2. And that should have been marked M sub 1. This is my mistake, but doesn't change anything. Anyway, the interior support section moment is 70% of M sub 0, and the exterior support section moment is 26% of M sub 0. These are the basics we discussed yesterday. Okay, so if it is an end span of a flat plate, the moment distribution is 70% at the first interior support, 26% at the exterior support. The 70 plus 20 adds up to 96. Half of that is 48. The remaining 52% is the bending moment in the span. So the M sub 1, the first interior support moment is 99.8 kilonewton meters. M sub 2, the exterior support section moment is 37.1 kilonewton meters. So we have all the numbers here now. V comes out to 114.3 kilonewtons. Okay, if we neglected this part, shear would have been 126.6. In reality, the shear is 114.3 kilonewtons. The shear stress on the critical phase, the plus gives us the largest shear stress, obviously. When it is minus on the opposite phase, that will be a lower shear stress. That shouldn't cause us any problem. So V sub U, this is the direct shear that we just calculated. A sub C is the total area of the three faces of the critical section. We are talking about an edge column with bending perpendicular to the edge. Then the moment transfer by shear divided by the polar moment of inertia multiplied by the distance from the centroidal axis to the face where we are calculating shear stress. Okay? So A sub C, the total area of the three faces is, we have two faces of length 484 meters, one face of length 568 meter. So the three faces together has a perimeter equal to that, multiplied by the thickness of the slab gives us A sub C of 0.26 square meters. Okay. Gamma sub F for our B sub 1 and B sub 2 is 0.62. 62% is transferred by flexion. That will leave 38% to be transferred by shear. And then remember, there was a major quirk. The exterior support section moment is 26% of M sub 0. But when we do shear calculation, the moment that we have to transfer is 30% of M sub 0. This is that particular section of ACI 318. So our transfer moment is 30% of M sub 0. M sub 0 we calculated earlier. So the 30% comes to 42.8 kilonewton meters. This is somewhat important. Okay, you do not transfer the end moment of 26% of M sub 0. You transfer a higher moment, 30% of M sub 0. That in our case comes to 42.8 kilonewton meters. So all we need, so in this expression, we have our B sub U, we have our A sub C. Okay, that part we can calculate. Gamma sub B is 0.38, M sub U is 42.8. What we do not have is our J over C. Okay. Now J over C, I think I copied I copied them again. Okay. So J over C, we have an edge column perpendicular to the edge. So we are talking about case C. For case C, here, J over C is given by this expression, 2b1 squared d, etc., etc. So we copied this expression, 2b1 squared d. Okay, this is a faithful reproduction of what you see in that box of the table. So 2b1 is 484, d is 168, b1 is 484, b sub 2 is 568, d is 168, b1 484, b2 568, b1 484. So all of that gives us a J over C of 0.0464. This is meter cubed. J is meter to the power 4. C is meter. So this is cubic meter. So the shear stress on the right section is V sub U over A sub C. V sub U is 114.3 divided by A sub C of 0.26. Gamma sub V is 0.38, 42.8 is M sub U. J over C is 0.464. All of that gives us 789 kilonewton per square meter shear stress. 789 kilonewton per square meters, that number. Okay. The phi times V sub C, phi is 0.75, V sub C is this is the 4 square root that we calculated. It's probably way back. So anyway, so V sub C, this is punching shear strength of concrete, remember, given by 3 different formulas. The smaller one governs. The smallest one in our case is the 4 square root of F sub C prime, and that comes to 156, 1560 kilonewton per meter squared. That is the punching shear stress carrying capacity of the concrete itself. That being larger than our V sub U, we are okay. Since shear stresses are already okay. So this is the end of this design. Then I have a pretty significant observation. Okay, make sure that so we calculated the combined stress on the face of the critical section. Okay, should I go back to the picture, or I don't know. Okay, so shear is the largest on this face of the critical section. Okay, this is the direction of analysis. So we calculated the direct shear stress on that section, that face of the critical section, V sub U over A sub C. And then we calculated the unbalanced moment that is transferred by shear, gamma sub V times M sub U. We took that moment, divided by the polar moment of inertia about the centroidal axis, and multiplied by the distance from the centroidal axis to this face. And that gave us the additional punching shear. The two together came out to The two together came out to 1506. No, I'm sorry, this is the strength. The two parts together came out to 789 kilonewton per square meters. Okay, the direct shear plus the moment transfer shear, 789 kilonewton per square meter. The punching shear stress that concrete can carry is 4 square root of f sub c prime. That reduced by the phi factor is 1.5, is 1560 kilonewton per square meters. This being larger than that, we are totally fine with respect to punching shear. Okay, and then I'm saying that we carried out this computation. This is very important. Okay, so our calculated value of gamma sub f is 0.62. We use that value, and that gave us a gamma sub v of 0.38, and we have no shear problem. We could have increased. This is an edge column bending perpendicular to the edge. We could have increased gamma sub f from 0.62 all the way to 1. That would have given us 0 moment transfer shear, and the shear stresses would have been even lower. But why would you do that? Because if we did that, if we took gamma sub f equal to 1, we would have to add reinforcement over the columns over the moment transfer band. Remember yesterday, I think we went from, I forgot the numbers, but we had to add at least 2 additional bars in order to go from gamma sub f of 0.62 to a gamma sub f of 1.0. Okay. So in this particular situation, with this example, since there is no shear problem anyway with a gamma sub f of 0.62, there is no point in increasing that to 1.0. Okay. So then the interior support section. This is in a way simpler, if you like. So you are familiar with all the dimensions by now. This part here is now plus, okay? Going by the figure that I showed you earlier, I will not try to go back. So V sub u is now this part plus that part, the end moments now add. So the V sub u is 250.3. All the dimensions and so forth, everything here should be familiar to you by now. The A sub C for an interior, well, A sub C, we now have 4 faces to the critical section, each equal to 568, and that is the depth. So A sub C is 0.38 square meters. J sub C, if you go back to the PCA chart, this is the interior, this is case 2. That is J over C. That comes to 0.738 meter cubed. So the transfer moment is very, very small. The difference between 70% of M sub 0 and 65% of M sub 0, that gives us 7.1 kilonewton meters. Gamma sub F is 0.6. Here, we could not even increase it if we wanted to, because V sub U is larger than 40% of phi times V sub C. So that option is not even there. An increase from 0.6 to 0.75 is not allowed because V sub U is larger than 40% of phi times V sub C. So our gamma sub V is 0.4. So the direct shear divided by the total area of the critical section, gamma sub v of 0.4, transfer moment of 7.1, J over C 0738 gives us 697 kilonewton per square meters. P times V sub C remains 1564 square root of F sub C prime, and we do not have a shear problem at the interior support. If you don't have a shear problem at the exterior support, you wouldn't have it at the interior support, but we still check. And that is the end of this study. Okay, I had hoped to get here by 10 or so. Anyway, I will still go to the other file because it has been bothering me that I could not. All kinds of things pop up, and it's okay. Can you still see my screen, Bodhi?
Yes, Dr. Ghose.
Yeah, okay, good. Okay, so there were two examples, 2 and 3, that I couldn't do the other day. One is lap splice is in tension. This will be lap splice in a beam. So this is a beam. This is the positive reinforcement. We want to lap splice the positive reinforcement. Obviously, we will do it where the bending moments are low, near the inflection point, definitely not near midspan. Okay. The section is shown here, 500 by 600 millimeters. We have 4 number 28 bars at the bottom, F sub C prime 440, F sub Y 420 MPa, M sub U, the required moment strength at that section is 100 kilonewton meters. Clear cover is 40 millimeters, 2-legged, number 12 stirrups. All that is given in the problem statement. Okay. Now, in order to calculate splice length, you have to calculate development length. Remember, for class A splices, the lap length is the development length. For class B splices, the lap length is 1.3 times the development length. The development length is given by this expression, and I don't know how necessary it is. So lambda is lightweight concrete factor. The size of T is top bar factor. Top bar is a bar having more than 12 inches in concrete cast in one lift underneath the bar. Okay, so for our bottom reinforcement, it is definitely other than top bar, so size of T is equal to 1. Epoxy coating factor is equal to 1. There is no epoxy coating. The bar size factor, size of S, is 1.0 for number 22 or larger bars. And K sub T R, the confinement index or whatever it is called, that can conservatively be taken equal to 0. So about the only thing we need now is the C sub B. C sub B is the smaller of two things: concrete cover from center of the right bar or the left bar, the bar that is nearest to the faces. So concrete cover from center of either the right bar or the left bar, it will be the same number. Clear cover is 40 millimeters. 12 millimeter is the diameter of the stirrup or tie or whatever there is, the transverse reinforcement, plus half the diameter of the longitudinal bar. That gives us 66. Also, half the center to center spacing of bars. Okay, 500 millimeter is the total section. We take 2 covers off from the 2 sides. 2 number 12 transverse reinforcement minus 1 bar diameter. There are 4 bars. Okay, so so there are three spaces. Okay. So so 500 is the total. We took the clear cover out from two sides. We took the uh, uh, two two times the diameter of the stirrup. Uh, I yeah, stirrup would be probably the right word. Okay, so and then we from each side we take away half the bar diameter because we want to go to the centers of the bars, and that will give us the center to center distance between the left bar and the right bar. And there are four bars, three spacings. So center to center spacing between the bars is this time, this divided by 3, that is 61 millimeters. This being smaller than that, C sub B is 61 millimeters. So the development length comes out to 776 millimeters. It cannot be any lower than 300. So 776 is our number. Okay. Now M sub U at the critical section is 100 kilonewton meters. So required moment strength would be that divided by phi, that would be 111 kilonewton meters. Okay. The effective depth is we have 600 millimeters total depth minus 40 clear cover minus 12 the stirrup diameter minus half the bar diameter, that's 534. Assuming a moment term of 90% of the effective depth, A sub S required, the tension reinforcement required to resist that much of moment would be the moment divided by the lever arm and the yield strength of the reinforcement. So we require 550 square millimeter of reinforcement. We actually provided 4 number 28 bars, and that has a total area of 2464 square millimeters. So A sub S over A sub S provided over A sub S required is 4.48. Okay. So 4.48 is definitely larger than 2. Also, using a staggered arrangement of splices and having only 2 bars spliced at the same location, only half of the total reinforcement is spliced within the required lap length. So if we satisfy both requirements, that A sub S provided is at least twice A sub S required, and that we do not splice more than half the bars at one section, then we can use a class A tension splice. So the splice length in our case is the same as the development length, which is 776 millimeters. So provide a splice length of 800 millimeters, this thing rounded off, staggered with a 600 millimeter spacing. The 600 millimeters is just picked as being reasonable. So this is what the splices would look like. 4 bars at the bottom of the beam. We will we lap. This is our lap splice, and then the next lap splice is staggered 600 millimeters, and then another one, and then another one. Okay? So this is a pretty nice, simple example that I think will help you. Beam splices. Okay. Now column splices. I discovered last night, actually, our time, that in order to explain the last example, I probably should go into this section of the code, 12.17.2, which in BNBC is 8.2.15.2. Okay. So this has a number of requirements where the bar stress due to factor load, this is specifically lap splices in columns. So where the bar stress due to factor loads is compressive, lap splices shall conform to section such as, anyway, the remainder is what is important. So where the bar stress due to factor loads is tensile, bar stress, these are column bars. Where the bar stress due to factor loads is tensile and does not exceed 50% of F sub y in tension, lap splices shall be class B tension lap splices if more than one half of the bars are spliced at any section, or class A tension splices if half or fewer of the bars are spliced at any section, and alternate lap splices are staggered by one development length. Okay, quite a bit said here. And it may be worth repeating. So where the bar stress due to factored loads is tensile, remember these are column bars, but the stress is tensile, but does not exceed 0.5 F sub y in tension. In that case, lap splices shall be class B tension lap splices if more than one half of the bars are spliced at any one location, or class A tension splices is if half or fewer of the bars are spliced at any one location, and alternate lap splices are staggered by the full development length L sub D. Okay. Next thing it says is where the bar stress due to factor loads is greater than. So stress is tensile and it is greater than 0.5 F sub y in tension. Now the lap splices have to be class B tension lap splices. Okay. Then in tied reinforced compression members, okay, compression members with ties, where ties throughout the lap splice length have an effective area not less than 0015 HS in both directions, lap splice length shall be permitted to be multiplied by 0.83, but lap length shall not be less than 12 inches. I should have changed that. The tie legs perpendicular to dimension H shall be used, etc. So this I will illustrate in the example. Okay. So if tied reinforced compression members where ties throughout the lap splice length have an effective area not less than something, we get a reduction factor of 0.83, 17% reduction in lap length. And then finally, in spirally reinforced compression members, lap splice length of bars within a spiral shall be permitted to be multiplied by 0.75. Now we get a 25% reduction, but cannot go below 12 inches. Okay. So this is our final example. We have this 500 by 500 column, 8 number 32 bars, F sub C prime 40 MPa, F sub Y 420 MPa. The splices are at the floor level. As long as design category is no higher than C, you can do that. If design category is D, then the splices have to be in the middle half of the column height. That is an additional complication. We will not go there today. So this lap splice length is what we want to calculate, okay, in this particular problem. There are dead loads, live loads, and seismic loads. Those are the applicable load combinations. 1.4 dead, 1.2 dead, 1.6 live. Then the additive seismic load combination and the counteractive seismic load combination. So From the different load combinations, we have these combinations of P sub U and M sub U. P sub U of 1873, no bending moment. P sub U of 2262, no bending moment. P sub U of 1864 coupled with a bending moment of 246. 1150 coupled with a bending moment of 246. Okay. So these are the P sub U, M sub U combinations. 1 and 2 have only axial load, no bending moment. 3 and 4 are the additive seismic load combination and the counteractive seismic load combination. Now for this column section, 500 by 500 column section with 8 number 32 bars, we have developed the load moment interaction diagram. This is typically done, can be done by hand, very laborious. This is typically done with computer programs that are available, and that's precisely what we have done. Okay, this is axial load on the x-axis and bending moment on the axial load on the y-axis and bending moment on the x-axis. This is compression, this way is tension, and the bending moments are, clockwise, counterclockwise, whatever. So under the first two load combinations, we have only compression in our column bars. So we can go for compression lap splices. Okay, nothing wrong with that. There was a question one of these days. Do column bars have to have, can column bars have compression splices? And my answer was only if under all the load combinations you have only compression. Here, under two of the load combinations, you have compression. And in those cases, you can have, for those load combinations, you can have compression lap splices, but you will not, how should I say, the splices that you provide will be governed by the most critical load combination. Okay, you will not do different splices for different load combinations. Now, load combinations 1 and 2, all bars are in compression. A compression lap splice is permitted in accordance with section such and such. Load combination 3, tensile stress in bars is less than 50% of F sub y. Here, 50% of F sub y is here. This way, we have more than 50% of F sub y. This way, we have less than 50% of F sub y. Here, there is no tension. From here on, this is compression. So 3 gives you less than 50% of F sub y. The 4 gives you more than 50% of F sub y tension in your bars. So tensile stress in bars is less than 50% of F sub y, assuming all bars are spliced at the same location. A class B splice is required. This is what I showed you earlier. And load combination 4, the stresses are more than 50% of F sub y, so you definitely need class B tension lap splice. So what we have to have is class B tension lap splice, and the splice length then will be 1.3 times the development length. Development length is given by this expression, and I do not know that I want to take you through the details. It's pretty routine calculation, and the lap splice length comes to 1182 millimeters. The minimum is 300 millimeters. So 1182, that's a long lap splice. Now here, remember there was a 17% reduction for tied columns, if the cross-sectional area of the legs exceeded, what was it, 0015 Hs. So this is the requirement. Okay, let's go through this. So we have, let me go back. We have 3 legs of ties provided in each direction. This, that, and that. This, that, and that. Okay. And so this said, in tied reinforced compression members where ties throughout the lap splice length have an effective area not less than 0015 Hs in both directions, lap splice length shall be permitted to be multiplied by 8.3. We have 3 legs of, I forget the diameter of that, 12, I think. 3 legs of number 12 bars in each direction. So 3 legs of number 12 ties are provided at 450 millimeter spacing. A sub B is 3 times 113, which is 339 square millimeters, and that is larger than 0015 times the H is 500, the total dimension of the section, times the spacing of 450 millimeters. This 0015 HS comes to 337.5. We barely made it, but we made it. A sub B is larger than that. So we get a 17% reduction. So the 1182 millimeters of lap splice length comes down to 981 millimeters, at least psychologically better. It's less than a meter. So provide 1 meter lap splice for the 8 number 32 bars at floor 1 level, assuming seismic design category is no higher than C, as I mentioned previously. Okay, so that is, I feel a lot better that we have now covered the development length topic to the extent that I thought that we should. Okay, so thank you very much. We will proceed to questions for the last, whatever, 25 minutes left. Obviously, if you have questions, and today's topic of two-way slab design for shear, and also if you want to go back to development length, I'm open.
Thank you, Dr. Ghose.
Okay.
Yeah, so there are some questions there. I've gone through some of them. Most of the questions today are related to some administrative part related to quiz.
Mm.
A lot of people were having some problems with the quiz that I have to look into in yesterday's quiz. Yeah, but that's not something major. It's very easy to fix that. The other questions related to seminar, like related to the webinar today, I will just go through one by one.
Mm-hmm.
Okay, starting from the latest ones. So in slab, which directions should we place the shrinkage and temperature reinforcement?
Read that again.
In slabs,
Mm.
in which directions should we place the shrinkage and temperature reinforcement?
Shrinkage and so in one direction you have flexural reinforcement, in the orthogonal direction you will place the shrinkage and temperature reinforcement where there is no flexural steel. That's the whole idea. If you have flexural reinforcement, then you don't need shrinkage and temperature. So one-way slabs, for instance, you have flexural reinforcement in one direction only. In the orthogonal direction, you will place the shrinkage and temperature reinforcement. We typically place the shrinkage bars on top of the bottom flexural bars and below the top flexural bars, if you can picture that.
Right. So there is one question that you addressed yesterday also, Dr. Ghosh. So that is the special moment frames with flat slabs. So as you mentioned yesterday that those slabs are not can. So there is one question related to that, saying that can we design those slabs as not a part of seismic force rating system?
Yes, as I answered yesterday, if you want to use flat plate column framing for a building assigned to seismic design category D, what you have to do is to combine the flat plate column frames with shear walls. The shear walls have to resist 100% of the lateral loads, and the flat plate column frames should be designed to carry all the gravity. And then you have what we call a building frame system. Very importantly, you have to satisfy deformation compatibility requirement. You have to make sure that the slab column frames will continue to carry full factored gravity loads as they deform together with the 100% lateral force resisting shear walls all the way up to the design earthquake displacements. So that is the way to utilize flat plate column framing in high seismic applications.
Right. So, Dr. Ghosh, I was checking I know the section that is in ACI that covers these topics, but I was checking BNBC, and the BNBC section 8.3.12 actually covers this section. And it actually mentions that for two slabs without beams, the slab column connections should meet the requirement of section 8.3.12.5. But I was checking, interestingly, that section doesn't exist. It just mentions that. So,
No. Well, we'll get there. We have several seismic lectures. I will emphasize this.
okay.
BNBC actually has a specific prohibition. You cannot do this, make the flat plate column frame part of the resisting system in high seismic design categories. ACI, there is no explicit statement, but I will show you why we cannot do that in reality.
So moving on. If the clear floor height is 2.5 meters only, the most common condition for column splice requires 1 meter. It seems inconsistent.
So what do you want to do? So you have shallow shallow floors, well, whatever. So 2.5 meters is pretty. I don't even know. They're not common here. Maybe, yeah. Anyhow, so your floor height is 2.5, and your lap is 1 meter, and you don't think that makes sense. I totally agree, but if that's what it is, that's what it is. So you want to decrease the laps, you have to go for thinner bars. Or if you don't like long laps, you have to go for mechanical splices, which cost a lot of money. That's another choice you always have. But the cost goes up. I agree. A 1 meter lap in a 2.5 meter floor
Yeah.
uh, doesn't make a whole lot of sense, but 2.5 is I don't know how usual it is, and if it is if the story height is that low, then I wonder why the lap is that long, because that indicates you are using very large bars. Why are you? So yeah. Anyway, so you have those two choices. Go for thinner bars, which will which will give you a shorter lap, or you know, mechanical splice is always a choice.
If there are two spans in one direction and three spans or more in other direction, how do we design the slabs?
I don't see any problem. Two span will mean that you cannot technically at least use the direct design method, but that doesn't mean you cannot design the slab. I do not see what the problem is.
Right. This
Yeah,
question is related to the
direct design method will not apply, but we will. There are computer programs available that most of them, I shouldn't say most, there are some that use the equivalent frame method, or more and more now, you design slabs based on finite element analysis, and the biggest selling program probably is CSI. What is it called? Safe. So that's what pretty much you will do.
right. Yeah, most of the programs nowadays they go into finite element analysis,
Yeah.
mesh the slab, and then
Yeah.
they do that.
Yeah, and then nothing matters. How many spans you have, what kind of column layout, so they calculate the stresses, and you reinforce according to where the tension stresses are is where your reinforcement goes.
Okay. Hard to understand this question. So there's one question related to the column lecture.
Hmm.
Should I read that or
Yeah, yeah.
okay? So when calculating moment capacity of a column section in different condition, moment has been calculated about mid-center of the section, except for pure flexure where neutral axis is used. Would you please describe the reason of selecting the center of the cross section?
Oh, he's talking about one of the examples. There is no
Example.
reason, and it doesn't make any difference at all. You take moment about anywhere, you will get the same result. I do not know why we did that. You know, but it does not make any difference whatsoever. You take moment about any section, you will get exactly the same results.
So the maximum spacing of reinforcement in slab is 2 times of H, that is the thickness of the slab.
Say that again.
The maximum spacing of reinforcement in slab
Yeah.
is 2 times the thickness of the slab.
How
For
many
beam,
times?
2 times.
Yeah.
For beam slab, we do not provide top reinforcement at the mid of the slab.
Hmm.
Should we provide reinforcement through at the top of mid slab?
What does it mean mid slab?
I'm not.
MID.
MID. Yeah.
So what he's saying is that in the middle part of the span there is no top reinforcement because the negative reinforcement has been cut off.
Oh, mid span of the slab. Okay, okay.
I
Understood.
think that's what he's saying.
Okay.
And the question is, should we have continuous reinforcement at the top? So if it is gravity design, you are not required to have continuous reinforcement at the top. So unless it is a seismic application, then we do, So maybe wait until the seismic lectures, and you will see that there are times when we do require continuous top and bottom reinforcement, at least in the column strip. But
Yeah. If
yeah,
it is mid span of the slab, then this question is clear. Mid of the slab was kind of confusing.
no, that's what he's asking. I'm pretty sure that the negative bars are cut off. So in the middle portion of the slab, there is no top reinforcement. Is that proper? And yeah, there is nothing. Yeah, that's what we allow. Yeah, definitely.
Okay. There's one very general question. So if we always check two-way share, so will it be so in what case should we check one-way share?
So read the whole thing again.
So the question is like, is two-way share is checking two-way share by itself is enough, or should we check one-way share also? Or that's what the question is.
It depends on what you are designing. So in a beam, there is no two-way shear. There's nothing, no two-way shear to check. One-way shear is what governs. Okay. So if it is a beam supported slab, there is there is no two-way shear to check unless they are very flimsy beams. So two-way shear we check in the design of column supported slabs, flat plates, flat slabs, two-way shear typically governs the design of those things. Should we check one-way shear in those cases? We typically do, but as I said, I have never seen that govern. We typically do, maybe because there may be an oddball case where the dimensions are such that one-way shear may cause problems. I do not know. It's very easy to check. We check, but I have never seen it govern. So it is, how should I say? There are many things we design where two-way shear is not a concern. It just doesn't develop. There is no two-way shear of any significance. Okay? And that is true of frame construction. Two-way shear is where there are no beams. And does one-way shear concern entirely go away? I'm not prepared to say that it does. Okay, we typically check it, but I would again say that it typically doesn't govern. So I don't know. Have I answered the question or no?
Yeah, you have.
Okay.
So is rebar coupling allowed in all seismic design categories?
Coupling,
Yeah,
mechanical, you mean?
yeah.
Yeah, it is allowed in all design categories, yes, including high seismic. Yes, absolutely.
Is there any provision in BNBC 2020 for reinforced brick concrete slab?
Reinforced brick. Uh, I I haven't I don't believe so, but then I mean I would like to check to come up with a more definite. Dr. Lucky would know. but let me, I haven't seen, frankly, well, let me say two things. Reinforced brick, the language is a little bit problematic in my opinion. Uh, Reinforcement requires holes in your masonry. The bars have to pass through holes in the masonry units. So typically, when we talk about reinforced masonry in this country, it is block masonry, concrete blocks that are reinforced. And blocks have cells, as you know. Clay brick without any holes in them cannot be reinforced. In the Western United States, there is hollow brick with holes that they use for reinforced brick masonry. That's the only part of the US where this is done. I do not believe in Bangladesh the clay brick comes with holes in them that you can reinforce them even if you want to. How much block usage there is, I do not know. Block can be reinforced, but I do not believe there is much usage of reinforced block masonry as far as I know. And I don't think there are provisions in the BNBC, but then, if Dr. Rakib is on the call.
Yeah, I checked. He's not there today.
Oh, okay.
Yeah.
Okay. So that's my answer.
Okay. So what will be the punching perimeter of lift core wall footing?
Punching perimeter of what?
Lift core wall footing.
Lift core wall footing. Again, I do not know why it is anything special. First of all, I don't know. Lift core means what we call elevator core, I think. So that will typically be a box like, so there will be shear walls on four faces making up basically a box, although there are openings for, people have to get in there. Now, this whole thing punching through is not something that anybody ever checks. So I don't know why the punching perimeter question arises. If it is the individual walls making up the core, that again, for walls we do not punching is not a concern for walls, it is for columns. So I do not know. I do not see the relevance of this question, frankly. Maybe I don't understand, but I do not.
He's talking about the entire lift core wall together, like
Yeah,
punching.
a lift core wall, a whole elevator core will not punch through. That is not
Right.
that's not a possibility. Maybe it is. I don't know. But if it is that the same principles will apply, you will take the whole box as a huge column, and you go one half of D away from the column face. What the D would be, I don't know. This will be strange calculation. I have never seen it done. Frankly, I don't know. I I I still think it is not something that an engineer will need to do.
Right. Yeah, I'm just going through the questions.
Mhm.
Whatever.
Mhm.
Uh, how to place headed shear studs in the footing?
How to place headed shear studs in the footing. Yeah, I don't know. Is the concern that it is upside down situation? Maybe that's what he's talking about. Then, yeah, I don't know offhand. Maybe I need to think a little.
I'm just keeping this question as high priority, so you can address it afterwards if needed.
Yeah, shear starts in the footing. I don't think are common. I'd like to find out a little. Yeah, I don't know. I'll make a note.
Dr. Ghosh, one question it was asked yesterday also. Probably I'm missing something. I don't know, but I'm. That question has been asked again. So
Mm,
in our country,
mm,
in flat plate construction,
mm,
some people use conceal beams. Is
mm.
it right or not?
Council beams then.
Is it right or not? Like they just want to know if the conceal beam methodology is common in Bangladesh or not.
I need to know quite a bit more to answer the question. I don't know. When you say concealed beam, it doesn't mean much. So I do not know enough to answer the question. I would like to know. So in this kind of a case, send something in by email with preferably a sketch or a drawing so that we understand what you are talking about. And then one can give opinion. I do not know enough to tell you. Unfortunately, I do not have the background to understand the question, so you have to provide the background.
Yeah. So for a flat plate system, a flat slab system, in order to do a faster calculation, can we consider a uniform slab thickness, that is flat plate thickness, plus the column capital?
What does that mean? Read that again.
For a flat slab system,
Hmm.
in order to do a faster calculation,
Hmm.
can we consider a uniform slab thickness of flat plate thickness and column capital?
The question is not making a lot of sense. The column capital is part of the column. It has nothing to do with the slab. So that part of the question is not understandable. I kept on
More
saying that.
context is needed. He's talking
Uh,
about something like more context is needed in this question in order to understand it.
well, no, he has two things. So he brings in column capital. Column capital is part of the column, does not enter into anything to do with the slab. And then he has a drop panel, but for simplicity in calculation, he wants to use an average thickness or something. That is an absolute no. The whole purpose of the drop panel is to make the slab thicker near the support, and then where that thickness is needed, you go for a thinner slab. How can you have to use the thicknesses that there are. There is no shortcut to that. No, I that does not make any sense whatsoever to try to use an average thickness. For what calculation?
Right.
So I don't know.
Okay. So other questions that I'm looking at are simply suggestions, mostly the answer related to concealed beams.
Okay, so this is
Yeah.
probably fairly common practice. So if somebody would kindly send us some information, we will we will try to form an opinion.
Dr. Ghose. So I think most of the questions are answered.
Okay.
And I think most of the questions actually, like today we got through most of them.
Okay.
And
Okay.
yeah, so questions related to flat slabs and like in high seismic areas and those things will be more clear, I guess, in your
Yeah. Yeah.
lectures,
Yeah. Yeah.
upcoming lectures.
Yeah.
So that will help a lot.
Yeah.
Um, so yeah, so we would end the webinar today. Yes.
Yeah. Yeah.
And people who are facing problems with the quiz, I don't know what exactly is the problem because I'm trying to recreate it myself here and I'm not getting that error. So people who are facing those problems, just send an email to support@prpportal.org. And I would suggest just close the browser, log, uh, and then sign in again to the portal and then check if the problem is persisting. Sometimes that's the problem. So just try that. And again, we would love your feedback for the session. And Dr. Ghosh is trying his best, and he has put a lot of effort in his slides and in his lectures. So your feedback will be really appreciated. And thank you so much, and see you tomorrow for the next webinar.
Yeah, thank you, buddy. And we are sorry this week it is 6 seminars in the week. It is way too much. We